Hey friends, welcome to the YouTube channel all about electronics. So in the previous videos of the differential amplifier, we have seen that how the differential amplifier amplifies the differential input signal and rejects the common mode input signal. And through qualitative analysis, we have also derived the expression of the differential gain. So in this video, through a small signal analysis, we will understand more about this differential amplifier. And at the later part of the video, we will also derive the expression of the CMRR. So this CMRR is the common mode rejection ratio, and this CMRR is the figure of merit for this differential amplifier, and it shows how well this differential amplifier is able to reject the common mode signal and is able to amplify the differential input signal. So for the small signal analysis, we will assume all the DC sources in the circuit as 0. That means this voltage source VCC will act as a short circuit, while this constant current source will act as a open circuit. And then after, we will replace this BJT by the small signal model. So after the replacement, the equivalent circuit will look like this. So basically, here we have replaced these two transistors by the small signal model. Now let's say the voltage at this node is equal to Vp. Now during our qualitative analysis, we have seen that when the differential input signal is very small, then this node P will act as a virtual ground. So through a small signal analysis, let us prove that. So if we apply the KVL in this particular loop, then we can write voltage Vin1 minus Vpi1 is equal to Vp. Similarly, if we apply the KVL in this particular loop, then we can say that Vp is equal to Vin2 minus Vpi2. And here this Vin1 minus Vin2 is the differential input voltage. Let's call it as the VID. So here let's say this Vin1 is equal to VID divided by 2, while this Vin2 is equal to minus VID divided by 2. That means here this Vin1 is equal to minus Vin2. Now if we apply the KCL at this node, then we can say that GM1 times Vpi1 plus GM2 times Vpi2 plus Vpi1 divided by Rpi1, that is this current, plus Vpi2 divided by Rpi2, that is this current, is equal to 0. So basically the summation of all these currents will be equal to 0. Now here, since the differential input voltage is very small, and assuming both transistors are perfectly matched, we can assume that this GM1 is equal to GM2, let's call it as GM, and similarly this Rpi1 is equal to Rpi2, so let's call it as the Rpi. So if we simplify this expression, then we can say that this Vpi1 plus Vpi2 times Gm plus 1 divided Rpi is equal to 0. Now we have just seen that this Vpi1 is equal to Vin minus Vp, while similarly this Vpi2 is equal to Vin2 minus Vp. That means from this expression we can write Vin1 minus Vp plus Vin2 minus Vp times Gm plus 1 divided by Rpi is equal to 0. And as we have seen, this Vin1 is equal to minus Vin2. That means here these two terms will get cancelled out, and the remaining term will be minus 2 times Vp times Gm plus 1 divided by Rpi, that is equal to 0. And that is only true when this Vp is equal to 0. So from this we can say that the voltage at this node is equal to 0. Or we can say that for the small signal analysis, this node will act as a virtual ground. And since this node will act as a virtual ground, so we can redraw the circuit like this. So now these two transistor circuits will act as a common emitter amplifier. So for this transistor Q1, this VO1 will be equal to minus Gm times V pi 1 times RC. And now, since this node acts as a virtual ground, so we can say that this V pi 1 is equal to V in 1. That means VO1 is equal to minus Gm times V in 1 times RC. And this V in 1 is equal to VID divided by 2. That means VO1 is equal to minus Gm times VID divided by 2 times RC. Similarly, this VO2 is equal to minus Gm times V pi 2 times RC. And similarly, over here, this V pi 2 is equal to V in 2. And this V in 2 is equal to minus VID divided by 2. That means VO2 will be equal to Gm times VID divided by 2 times RC. That means differential output voltage, that is VO1 minus VO2 will be equal to minus Gm times VID divided by 2 times RC minus Gm times VID divided by 2 times RC. That is equal to minus Gm times VID times RC. And the differential gain AD, that is VOD divided by VID, or the differential output voltage divided by differential input voltage, will be equal to minus Gm times RC. Now many times the input is only applied at the one end and the second end is grounded. And it is the case of the single-ended input and the differential output. So in this case also, the differential gain will remain the same. So let us see how. So in this case, the small signal equivalent circuit will look like this. So once again, if we apply the KVL in this outer loop, then we can write V in 1 minus V pi 1 plus V pi 2 is equal to 0. Or we can say that V in 1 is equal to V pi 1 minus V pi 2. And as we have seen, this VO1 is equal to minus Gm times V pi 1 times RC, while this VO2 is equal to minus Gm times V pi 2 times RC. That means differential output voltage VO1 minus VO2 will be equal to minus Gm times RC times V pi 1 minus V pi 2. And this V pi 1 minus V pi 2 is equal to V in 1. That means differential output voltage VOD will be equal to minus Gm times RC times V in 1. Or from this we can say that this differential output voltage VOD divided by V in 1 is equal to minus Gm times RC. And in this case, if you see, this differential input voltage VID is equal to V in 1 minus 0. That means VID is equal to V in 1. So we can say that in this case, this differential gain, that is VOD divided by VID, is equal to minus Gm times RC. That means in this case also, the differential gain is equal to minus Gm times RC. And the same is true if we apply the input at the other end and ground this left hand side. Now so far we have discussed the case of the differential input and the differential output, as well as the single-ended input and the differential output. But now let us see the differential gain when the input is differential but the output is measured only at the one end. So in that case, the gain will become half. So let's say the output is measured only across this VO1. So in this case, this differential gain will be equal to VO1 divided by VID. Now here, this VO1 is equal to minus Gm times RC times V pi 1. Or we can say that it is equal to minus Gm times RC times V in 1. And here we have assumed that this V in 1 is equal to VID divided by 2. That means VO1 is equal to minus Gm times RC times VID divided by 2. That means if we see this differential gain, then it will be equal to VO1 divided by VID, that is equal to minus GM times RC times VID divided by 2 divided by VID, that is equal to minus GM times RC divided by 2. That means in this case, when we take the single-ended output, then the differential gain will become half. So basically, we are not utilizing the swing of this other side. So that is the one of the disadvantage of taking the single-ended output in case of this differential amplifier. The other disadvantage we will talk little later. Now, so far during our discussion, we have assumed that the differential amplifier is biased using the constant current source. But when it is biased using the resistor, then in that case also, the expression of the differential gain will remain the same. So in that case, the small signal equivalent circuit will look like this. And by following these steps, we can find the differential gain. So here, the procedure is very similar to the procedure which we have followed earlier. And if required, you can pause the video and check the following steps. Now in the previous video, during the large signal analysis, we have discussed that the differential amplifier works as an amplifier only when the differential input is very small. But the range of this differential input can be increased by adding the emitter resistor at both transistors. But the drawback is that the differential gain of the amplifier will reduce. So let us understand it using the small signal analysis. So in this case also, this node P will act as a virtual ground. And with that, the small signal equivalent circuit will look like this. Now here, if you see the individual transistor, then it acts like a common emitter amplifier. But here, it is the case of the common emitter amplifier with the emitter resistor. And in one of the earlier videos, we have already derived the expression for this particular case. So for more information, you can check that video. That means in this case, the voltage gain will be equal to minus RC divided by 1 over GM plus RE. And the differential gain is also same. Now here, if this resistor RE is 0, in that case, the gain is equal to minus GM times RC. But because of this emitter resistor, the gain will reduce. So that is the effect of this emitter resistor. So now let us find the input impedance of this differential amplifier. So to find the input impedance, we will apply some voltage source Vx between the two inputs of this differential amplifier. And we will find the current Ix. And the ratio of this Vx and the Ix will give us the input impedance. So let's say the current which is supplied by this voltage source is equal to Ix. And the same current will also return to this voltage source, that is equal to Ix. So if we apply the KVL in this outer loop, then we can say that voltage Vx is equal to V pi 1 minus V pi 2. And here voltage V pi 1 is equal to Ix times R pi 1, while voltage V pi 2 is equal to minus Ix times R pi 2. Because here this current Ix is going away from this R pi 2. So from this we can say that voltage Vx is equal to Ix times R pi 1 minus of Ix times R pi 2. And here we are assuming that this R pi 1 is equal to R pi 2 is equal to R pi. That means Vx is equal to 2 times Ix times R pi, or the ratio of this Vx and the Ix, that is the input impedance, is equal to 2 times R pi. That means the input impedance of this differential amplifier is equal to 2 times R pi, where this R pi is equal to beta divided by Gm. Alright, so far we have found the input impedance and the differential gain of the amplifier in the different configurations. And during our discussion, we have assumed that the amplifier completely rejects the common mode signal. That means the output due to the signal which is common to the both input is equal to 0. And even if this common mode input signal changes, then also there won't be any change in the VO1 and the VO2. But that is only true if this current source is the ideal current source, or in other words, when the output impedance of this current source is infinite. But if this output impedance is finite, then the output voltage VO1 and the VO2 will respond to the change in the voltage VCM. But of course, if both transistors are matched perfectly, then the change in the voltage VO1 and the VO2 will be same. Or in other words, if we see the differential output voltage, then still it will be equal to 0. But if we see the single-ended output or the output only across the one particular terminal, then for this non-ideal current source, we will get some finite change in the output if there is a change in this common mode input signal. So now, let us see the single-ended output when this common mode input signal is present at the both input terminals and this current source is non-ideal. So basically, we are finding the single-ended output when there is a small change in this common mode input signal, and by doing so, we will find the common mode gain. And to find that, first of all, let us draw the small signal equivalent circuit for this particular case. So if we see the small signal equivalent circuit, then it will look like this. So here, this resistor RE is the output impedance of the current source. Now here, since both transistors are matched perfectly and the input to the both terminal is same, so we can assume that this V pi 1 is equal to V pi 2 is equal to V pi, and this GM1 is equal to GM2 is equal to GM, and of course this R pi 1 is equal to R pi 2 is equal to R pi. So assuming this, if we apply the KVL in this outer loop, then we can say that the common mode voltage VCM is equal to V pi 1 plus Vp, where this Vp is the voltage at this node. And here, this current is the base current, while this current is the collector current. And the current which is coming out of this node is the emitter current. The same is true for this second transistor. This current is the base current, while this current is the collector current. And the current which is coming out of this node is the emitter current. So from this we can say that the voltage Vp is equal to 2 times emitter current times RE. And here this emitter current IE is the summation of this base current and this collector current. That means emitter current IE is equal to V pi divided by R pi, that is the base current, plus GM times V pi, that is the collector current. That means Vp is equal to 2 times IE, that is equal to V pi divided by R pi plus GM times V pi times RE. That means Vp is equal to 2 times RE times V pi times GM plus 1 divided by R pi. Now as you are aware, this R pi is equal to beta divided by GM. That means 1 over R pi will be equal to GM divided by beta. And since the value of the beta is very high, so we can assume that this 1 over R pi is much less than GM. So approximately we can say that this Vp is equal to 2 times RE times V pi times GM. So now this common mode input signal, that is VCM, can be given as V pi plus Vp, that is equal to V pi plus 2 times RE times V pi times GM. Or if we further simplify it, then we can say that it is equal to V pi times 1 plus 2 times GM times RE. So this will be the expression of the common mode input signal. And here this VO1 is equal to minus GM times V pi times RC. And from this we can say that the common mode gain, that is VO1 divided by VCM, is equal to minus GM times RC times V pi divided by V pi times 1 plus 2 times GM times RE, that is equal to minus GM times RC divided by 1 plus 2 times GM times RE. Or if we further simplify it, then we can say that this common mode gain is equal to minus RC divided by 1 divided by GM plus 2RE. Now here, if this emitter resistor is infinite, in that case, this common mode gain is equal to 0. That means even if there is a change in this common mode input signal, then there won't be any change in this output voltage. But because of the finite value of this output impedance, we will see some change in the output voltage because of the change in this common mode input signal. And the change in the output voltage VO2 will be similar to the VO1. That means VO1 and the VO2 will change in the same way. Or in other words, if we see the differential output voltage, that is VO1 minus VO2, then it will be equal to 0. That means as far as both transistors are perfectly matched, then the differential output voltage, because of the change in this common mode input signal, will be still 0. But if there is any mismatch between the two transistors, then we will also see some differential output voltage due to the change in this common mode input signal. So let's say for this transistor Q2, the collector resistor is equal to RC plus delta R. So because of that, if we see the common mode output voltage, that is VO2, then it will be equal to minus GM times VCM times RC plus delta RC divided by 1 plus 2 GM times RE. So here, this output voltage VO2 is due to the change in the voltage VCM. So let's denote it as a VO2 CM. Similarly, the change in the output voltage VO1 or VO1 CM is equal to minus GM times VCM times RC divided by 1 plus 2 GM times RE. Or if we see the differential output voltage, that is VO1 CM minus VO2 CM, that is equal to minus GM times VCM times delta RC divided by 1 plus 2 GM times RE. Or if we see the common mode gain, then this common mode gain can be given as minus GM times delta R divided by 1 plus 2 GM times RE. Or we can say that it is equal to minus delta R divided by 1 over GM plus 2 RE. Now here, this 1 over GM is very small compared to this output impedance. So approximately we can say that this common mode gain is equal to minus delta R divided by 2 RE. Now here, if we measure the output voltage VO2 minus VO1, then this sign will be positive. So to just remove the ambiguity, let us take the magnitude. That means the magnitude of this common mode voltage gain will be equal to delta R divided by 2 RE. Now in this case, if we see the differential gain, that is AD is still approximately equal to minus GM times RC. Or if we just take the magnitude, then this differential gain will be equal to GM times RC. And as I said earlier, this CMRR or the common mode rejection ratio is the ratio of this differential gain to the common mode gain. And it shows how well the circuit is able to reject the common mode input signal. So in the ideal case, the common mode gain should be equal to 0. Or in other words, this CMRR should be equal to infinite. But actually, the value of the CMRR should be very high. So in this case, if we see the value of the CMRR, then the expression of the CMRR will be equal to GM times RC divided by delta R divided by 2 RE. Or we can say that it is equal to 2 times GM times RE divided by delta R divided by RC, right? So from this, as you can see, for the CMRR to be very high, the value of this RE should be very high and the value of this delta R should be very small. That means whenever the differential pairs are matched perfectly and the output impedance of this current source is very high, at that time the value of the CMRR is very high. Now assuming both transistors are matched perfectly, if we take the differential output, then the common mode signal gets eliminated from the output, right? But at some point in the circuit, we need to take the single-ended output so that we can connect the load to the output. For example, in case of the op-amp, although the input is differential, but the output is single-ended. So at some point in the circuit, we need to do the differential to single-ended conversion. The easiest way is to take the output from only one side. But as we have seen, in case of the single-ended output, the differential gain becomes half. Moreover, if the current source has the finite output impedance, then the common mode gain will also be the non-zero. So because of that, the value of the CMRR reduces. So in such case, to increase the CMRR, the active load is used with this differential amplifier. And in fact, in the integrated circuits, for this differential to single-ended conversion, usually the differential amplifier is used with the active load. So if you want to know more about it, then let me know in the comments. But I hope in this video, through a small signal analysis, you understood the different aspects of this differential amplifier. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.